Hello everyone, welcome back. Today we will look into the Leetcode easy level problem called Invert Binary Tree. The problem statement mentions that we have given the root of the binary tree. Using that root of the binary tree, we need to write a logic to invert the tree and return the root of inverted tree. So let's understand with the example. Let's take this binary tree as an example. For this binary tree, its inverted tree looks like this. If we closely observe the input binary tree and its inverted tree, we can see that in a given input binary tree, if we swap the left and right child for each node in that input binary tree, then that input binary tree gets converted to its inverted tree. How? For example, if we start with the node 4, if we swap its left and right child, then the tree will look like this. Then for node 7 and node 2, if we swap their left and right child, the tree will look like this. For the node 9, 6, 3 and 1, there are no child nodes or left and right nodes, so we can skip them. Now you can see that the input binary tree now became equal to its inverted tree. So simply if we swap the left and right child for each node in a binary tree, we can get its inverted tree. So using that fact, our approach will look like this. We need to traverse each node in a tree. Why? Because for each node, we need to swap its left and right child. So we need to traverse each node in a tree. For each node, make its current left child as a new right child. So this left child will become right child. Make its previous right child as a new left child. We can store its reference to some temp variable and make the previous right child at its new left child. Basically swap it. We can use DFS or BFS to traverse all the nodes in tree using iterative or recursive solution. So we can use DFS or BFS, both the approaches here, to traverse the nodes in a tree. So what we can do, we will use BFS for iterative solution and we will use DFS for recursive solution. Now let's understand the DFS recursive solution. So if we want to break down this problem, why we are using the recursion. So if you see, if we start with the big problem, which is inverting this binary tree, right? It can be divided into smaller problems with a recursive calls. For example, to get the inverted tree for this big tree, we can first get the inverted tree for its subtrees. And then again, for the next recursion, we can divide it further, like get a inverted tree for this highlighted subtree. So with each recursive call, we can divide the big problem of finding the inverted tree for whole tree into smaller problem of finding the inverted tree for the subtrees. So to invert whole tree, we need to invert its subtrees. For each recursion call, we can divide the tree into subtree till we go to our base case, which is our leaf node, because for leaf node, there are no further subtrees, right? Once the left and right subtree for node inverted, we can simply reverse the left and right child of the node. For example, for this whole tree where 4 is the root, if its left subtree and right subtree is inverted, then we can just simply swap left and right child of the 4 so that we can get the inverted tree for the whole tree. So the problem itself is a recursive in a nature. That's why we can use the recursive solution here using DFS. To visit all the nodes in our input tree for our DFS recursive solution to invert the binary tree, we can use any of the sub technique like in order, pre-order, or post order. But specific to this invert binary tree problem, post order is more clean and simple. So we'll go with the post order. You can implement using in order or pre-order also. If you implement it, please share it in the comments. So let's understand the DFS recursive solution implementation. So this is our invert tree function. If the root is null, return null. This is our base case. And in a post order, we know that we go to the left first and then we go to the right and then kind of visit the node or have a specific inversion logic for this problem. So let's start. So the invert tree will be called with the root of the whole tree, which is 4. So the invert tree function call with the tree node 4 as a root will be added to the system stack. And then we'll go to the left side. What is the left child of the 4? It is 2. So the invert tree function will get called with the tree node 2 as a root. Now, basically the invert tree function is getting called in a context of this subtree where 2 is the root. Now we'll again go to the left of that, which is basically invert tree with tree node 1 as a root. So this invert tree function is now executing in a context of this subtree where 1 is a root. Now we'll again go to the left of it. So which is root dot left is 1 dot left is null. So basically it will just return null. Where it will return? It will return to previous function execution, invert tree with a tree node 1 as a root. And it will store that null into this left variable. And then it will go to the right side of it. So 1 dot right is null. So invert tree gets called with the null. It will return because that is our base case. It will return where? It will return to previous function execution, which is invert tree with the tree node 1 as a root, basically for this subtree. And it will store the null in the right because right child of the 1 is null. Now we completed left and right for this subtree. Now we'll have a swap logic. Now left and right child of the 1 are null only. So 1 dot left, we are adding null, and 1 dot right, we are basically equal to null. So there is no left and right child, so there is no impact here. And we'll return the root. Root is this one, node 1. It will return where? It will return to the invert tree function execution, where node 2 is the root, basically for this subtree context. Now where it will return node 1 reference to this left variable, and it will go to the right side. Right side is invert tree with a tree node 3 as a root. Basically now invert tree is getting executed with this subtree as a context. Now for 3 it will go to the left, but the left is null, so it will return that null is stored into the left. It will go to the right. So on the right side also it is null, so the null will be stored into this right, and we'll come back to the invert tree function execution with node 3 as a root. We'll swap. Basically here left and right are null only, so there is no actual swap, and we'll return the node 3 from that invert tree function execution with tree node 3 as a root. Where it will return to the previous invert tree function with a node 2 as a root, and it will store the reference of node 3 into the right variable because we came from the right side. Now it will do swap here. What is root dot left? Root dot left, which is 2 dot left, it will add right. What is right? Right is 3. And root dot right, so in root dot right it will add left. What is left? Left is a reference of 1. So the tree will become like this, and it will return the node 2 to the previous function execution, which is invert tree with node 4 as a root, basically this whole tree. Now we completed the left. In a left, we will store the reference of node 2, which we got from the previous function execution. Now we will go to the right. So right child of the node 4 is 7. So we are executing the invert tree function with node 7 as a root, basically for this subtree context. And then we'll go to the left of it, which is node 6. Node 6 as a root. Now we'll go to the left of it, which is null. We'll come back, and it will store the null in the left side. Now it will go to the right side of the node 6, which is also null. So it will return, and we'll store that null reference into the right. So we are now swapping the left and right child of the 6, which is nothing but the null only. So no impact. And we'll return the node 6, which is the root, to the previous function execution, which is basically invert tree with a node 7 as a root. Now where it will return here, left side, because we are coming from the left. So left will store now the reference of 6. Now we'll go to the right side of the node 7, which is node 9. So invert tree will be called with node 9 as a root. Now the invert tree is getting executed for this subtree context where 9 is a root. For 9, it will call the root.left, which is null. It will return and store the null in a left variable. And then it will call right, which is also null for the node 9 as a root. So it will return and we will store null in a right side. Basically right variable. So left and right are null for node 9. We are in the invert tree function execution for node 9 as a root. And we will swap the left and right child of the 9, which are null only. So no impact. And we will return the node 9. Where it will return? It will return to the previous function execution, which is for this subtree where 7 is the root. And where it will return here. So we'll store node 9 reference into the right variable because we are coming from the right side. Now it will swap here. What is the right variable? It is reference of node 9. It will be stored on a root.left, which is 7.left. And left variable contains the reference of node 6. It will be stored onto the root.right, which is 7.right. So the nodes will be swapped and will return the node 7 to the previous function execution, which is invert tree with a node 4 as a root for this whole tree. Now we saw that the subtrees for left subtree and right subtree for this node 4 are inverted, right? So we divided this whole tree into subtree problem for invert logic. Now we completed the inversion for the subtree. Now we just need to simply swap the left and right child for the 4, and which is nothing but this logic, and the tree will look like this. So this is our output, the inverted tree for our input binary tree. And we completed that swap and we will return the root, which is node 4. And we completed the execution. So this is the DFS recursive solution to invert the given input binary tree. Now let's understand the BFS iterative solution. We can implement the iterative solution using DFS also. But just to cover both DFS and BFS for this problem, we are implementing the iterative solution using BFS. So we know that in a BFS means that it is first in, first out. Basically, first level gets visited first. That's why we are using queue here. So initially, the queue will contain the root of the tree. So this while loop will continue till we have some node to visit. Now, queue is not empty, so it will basically dequeue from the queue, which is 4 will be stored into the current, and it will swap the left and right child for the node removed from the queue. So 4 is removed. Now we will swap 2 and 7, basically left and right child of the 4. So the tree will look like this. Now for node 4, is there a left and right child? Yes. So we'll add them to the queue. So now the left child of the 4 is 7 now because we completed the swap first. So 7 node gets added to the queue. And the right child of the 4 is 2. So that will also get added to the queue. Now we'll come back to the beginning of the while loop again. We'll remove the node from the queue, which is first in, first out, which is node 7. We'll remove it and then swap the children of the node 7. Basically, we remove the node 7. Now we are storing the left point of the 7 into temp, and then left equal to current.right. Basically 7.left equal to 9 and 7.right equal to temp, because we are storing the reference of left node in the temp variable for swapping logic, and we are completing the swap. For 7 we have left and right child, so we'll add them to the queue, 9 and 6. Now we'll again come back to the beginning of the queue, while loop. Now queue is not empty. We'll remove the first element of the queue, which is 2. For 2, same swapping logic. We'll swap the left and right child of the queue using temp variable and then we'll add the children of 2 to the queue, left and right children of the 2, which is 3 and 1. Now we'll come back to the beginning of the while loop again. Now node 9 we will remove. For node 9 there are no left and right child, so we are just swapping nulls here. There are no left and right child, so we'll not add anything to the queue. Similarly, for other leaf nodes also, where there are no left and right child, so we'll not add anything to the queue, and we'll keep on dequeuing from the queue, and the queue is empty. It means that we visited all the nodes in a binary tree, and we got the inverted tree for our input binary tree using BFS iterative solution. So this is the implementation using queue to invert the binary tree. So this is the Java implementation for our DFS recursive solution, which we understood just now in a detail. The time complexity of this solution is, let's say we have n number of nodes in a binary tree, which we need to visit because we need to visit all the nodes in binary tree. So let's say if n is the number of nodes in a binary tree, then the time complexity will be O of n. Now let's submit this solution. So we can see that it is submitted successfully. Hope you understood the explanation about the problem statement and the different approaches we discussed. And more importantly, what was our thought process to come up with the different approaches, whether it is recursive approach or iterative approach, whether it is using DFS or BFS, how the recursion helps to solve this problem, and what is the time complexity of the solution, etc. If you like the video, please share and subscribe. Thank you so much.